We restated the strengthened Hahn-Neumann conjecture. Restatement. The restatement was in terms of the reduced rank of a graph rather than in terms of reduced ranks of a free group. So if x, y, z are finite graphs, and S is the fiber product. Fiber product of y and z with respect to, so usually we say fiber product of two graphs, but actually what's implicit here, it's not only of graphs but together with maps. Right? It is assumed that we have two maps. So with respect to some immersions, we assume that those maps are immersions. Immersions, let's call it alpha. Alpha goes from y to x, and beta goes from z to x. Then the restatement of the strengthened Hahn-Neumann conjecture has this nice short form. It says that the reduced rank of S is at most the reduced rank of y times the reduced rank of z. So S is this product. This is alpha, this is beta, mu and nu. So there are induced maps. You remember, every vertex in S is a pair of vertices, one and y, one and z, which map to the same vertex in X. Yeah?
Fundamental groups of S, fundamental groups of y, fundamental groups of z. You just think of fundamental group of S.
When you
last time we defined the reduced rank not only for groups but for graphs as well. This is the notion that I'm using. This S does not have to be connected, and we saw an example, even if y and z are connected, S does not have to be connected in general. So the notion of fundamental group, yes, one could restate, and this was the original algebraic statement of the strengthened Hahn-Neumann conjecture due to Walter Neumann. He stated in these algebraic terms. But this is the kind of topological translation of the same statement. And it's convenient because it has this nice short form, and also because the fundamental group, you see, you would have to talk about the fundamental group of each component. I mean, it's a correct restatement, but this is kind of shorter to write. Right? We define a notion, which is defined not only for connected graphs, but for arbitrary finite graphs. So it's a topological way. And this diagram, this is an example of is due to Stallings, and the ideas were by Imrich as well in a paper before. So this reduced rank is actually a concept. It has a meaning, and I will talk about this later on. It has a kind of independent meaning coming from analysis. But so far, let's see how one can try to prove this conjecture. Right? So first of all, there were many results kind of approximating. First of all, there was this Hahn-Neumann theorem. And you remember the statement was almost the same as the conjecture, except that there was this term 2, multiplication by 2. It can also be restated in these forms. So at that time she didn't talk about the strengthened version, because strengthened version was not there yet. It was introduced later on by Walter Neumann. But one can actually rewrite, one can actually just use that theorem and see that the same thing will hold for the strengthened version as well. So if one puts here number 2, then by the same argument one can prove that the statement is correct. So the theorem implies not only the Hahn-Neumann conjecture with up to like constant 2, multiplicative constant 2, but also the strengthened version would also imply that. It implies that the reduced rank of S is at most 2 times the reduced rank of Y times the reduced rank of Z. And the fact that it implies this was later on due to first, in a paper of Stallings, he introduced this way of thinking of the problem. And then in a paper by Gersten, he essentially did this. So he proved the strengthened version of Hahn-Neumann theorem, which means if you multiply by 2, then the statement is correct. And what is roughly the idea? So how one can try proving this theorem, strengthened version of the theorem first. One can notice that the reduced rank is almost the same as the negative Euler characteristic of the graph, roughly speaking. If we just concentrate on one component, say it's connected, then if this component is sufficiently large, meaning that if it's not a tree, in the case of a tree, the fundamental group is trivial. And that's where the rank becomes 0. The rank of the trivial group is 0. And that's kind of an exceptional case one has to deal with. Right? But if you assume that's not the case, then most of the time the reduced rank is essentially the negative Euler characteristic. But where most of the time is exactly the trouble, right? I mean, it's only in that exception where you get into trouble. But let's avoid this for a while, and let's just assume this graph is not a tree. So it's like a circle maybe, or like something like this. It has several loops, not just. It has at least one loop, maybe more, in it. Then one can pick x in a good way. And namely, one can take, for example, this graph with 2 vertices and 3 edges. Or, for example, one can pick 1 edge, 2 vertices, and then 2 loops on them. So either one of these, they represent the group F2. The fundamental group is the free group of rank 2. And but notice now that the valence of vertices is 3 of all of them. So valence is 3. So what is the Euler characteristic of this? 3 edges minus 2 vertices. The negative Euler characteristic would be 3 edges minus 2 vertices. So it's 1. And that's the same as the reduced rank. The reduced rank is 1 in each case. But that also happens to be the negative Euler characteristic of this x in this situation. If this is x, say, or this is x. And then, since one can see that this Euler characteristic can be represented actually combinatorially in terms of valence. This happens to be the same thing as 1/2 plus 1/2. Where 1/2 is, so let's write it down. It's the same thing as 3/2 minus 1 plus 3/2 minus 1. So what's the reason for writing this? 3 is exactly the valence here, the valence of the vertex. And minus 1 is just we subtract, because there is one vertex. So the idea is you take the valence of the vertex, you divide it by 2, and then subtract the number of vertices, which is 1, at this vertex. Right? And then you add up over all vertices. There are 2 vertices, so we add this up twice. That's roughly the reason. So there is a general formula for the negative Euler characteristic of the graph. You take, if provided that the graph has valence, say, 3, then you just consider the number of vertices of valence 3, For each of those vertex, you take this number. There is a formula. There is a general formula of computing Euler characteristic in terms of valence. And this is a special case of it. If all the vertices have valence, say, 3 or 2 or 1, then this formula works. It gives you a bound. Maybe if we assume that all valences are either 3 or 2, then the Euler characteristic is just the number of vertices of valence 3 divided by 2. This is 1/2 here. So I just took 2 vertices and I added 1/2 for each vertex. So once again, if the graph has valence 3 or 2 all the time, then the negative Euler characteristic is just the number of vertices of valence 3 divided by 2. But this divided by 2, that's where the main trouble is. That's how you get this number 2 eventually here. It doesn't let you to. But the idea roughly is that if you count the number of vertices of valence 3 here, and then if you represent the subgroup by an immersion, the valence of all these vertices will also be at most 3. And if there is a vertex of valence 1, then you can erase this. So if you have some graph and you happen to have a vertex of valence 1, then you can just remove this edge. And so you just remove this. And you reduce the graph until all the vertices have valence 3 or 2. And then you essentially count the number of vertices of valence 3. You count them here. And then in the fiber product, you also see that all the vertices of valence 3 will correspond to pairs of vertices. One vertex here, and both should be of valence 3. There is no other choice. So that's roughly the idea. The idea is that combinatorially you can actually prove this using the fact that you can express the Euler characteristic as the number of vertices of valence 3. But then you get this additional term 1/2, and that's how. Okay, maybe that's good enough, right? The question is, can we actually remove this number 2? Maybe it's not possible at all. Maybe there is some fiber product which realizes this. Maybe this, in other words, this upper bound on the intersection, on the fiber product, maybe it's the best possible. And the answer is no. There are easy examples showing that the equality can be achieved. And here is one example. Example, a ladder of length n, let's call it m, say, of length m is the graph. It's the following graph. You take 2 circles, one circle and then another circle, and you subdivide each circle into m parts. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then you connect them by an edge in those parts. So this is the ladder of length 5. One can do it for any m. Let's call it L sub m. The question is, say, as an example, let's take L1. Consider L1. What is L1? The ladder of length 1. You do the same thing. You take a circle, then take another circle, and you subdivide each circle into one part. So it's like this. And then you connect the vertices of the subdivision by one edge. The first question is, what's the reduced rank of L1? Exercise. So what was the definition? It's the usual rank minus 1. Or equivalently, it's the negative Euler characteristic, provided it is not 0. It is not, provided the Euler characteristic is not 1. So provided the negative Euler characteristic is not minus 1. So what is it? What's the Euler characteristic of this? -1, and then we take the negative Euler characteristic, so this is 1. What's the reduced rank of Lm? What's the best way to compute this? Of course, one can do it by hand, right? You compute first the rank, and then subtract 1. That would work. So what is it? It happens to be m, right? Like in this example, number 5, remove this edge, remove this edge, remove this edge, remove this edge. But then only one edge is left, and what should we do with it? We can still remove one edge and reduce the rank, but then it becomes 0. Sorry. Then we remove one more edge, and then the rank becomes 0. So by removing m plus 1 edges, you can make the usual rank to be 0. Right? You can remove, say, this, and there are many choices here. Right? 1, 2, 3, 4. Say these ones, and then you remove this edge, and you also remove this edge. So this edge just stays. Either way you count, it's the usual rank is m plus 1. Then the reduced rank would be m. But this is not the best way to count the rank. The better way is to note that this graph actually covers this graph. There is a covering map. Do the same thing. 1, 2, 3, 4, 5. Then there is a map from this graph to graph. You just it's 5 times, 5-fold. You can find. So what is the map? You take this circle and you wrap around this circle 5 times, and do the same thing for the other circle. 5 times cover, and then you know that. So exercise. The reduced rank of a graph is multiplicative under coverings. Multiplicative meaning that if you have a 5-fold covering, then and you know the reduced rank of this, then this would be just 5 times the reduced rank of this graph. It's multiplicative by the multiplicity constant. So it's an exercise to check, and how do you do it? If your graph is complicated enough, if this graph is not a tree, then the Euler characteristic would be at least 0. The negative Euler characteristic would be at least 0. And in that case, and the reduced rank is the same as the Euler characteristic. And we know that Euler characteristic is multiplicative. So in that case, everything follows. And then you need to separately again to consider this case when the Euler characteristic, the negative Euler characteristic is -1. And that means that the usual Euler characteristic is 1. And that means that say if the graph is connected, then it's a tree. It must be a tree. It should not have any loops. And you treat that case separately. Any covering of a tree must be the same tree, or maybe several copies of tree if you allow. But it must be just several copies of the same tree. So you treat that case separately. That's pretty much the proof of this exercise. So in particular, I can take this example. Take m to be 3. Let's call it Lm. I'm drawing I'm making a general statement, but I'm drawing a picture in the case when this is 3. And there is a covering map to L1. And here we take the graph, the ladder of length 2. Again, you can think of this being a general case for some n. There is a 2 times cover from here, and there is a 3 times cover from here. The question is, as you see this picture now, we can complete it to a fiber product diagram, right? And see what the fiber product is. What is this equal to? We can think of just one circle. Think of this circle just mapping to this circle 3 times, wrapping 3 times. And think of this circle here mapping to this circle 2 times. And try to find the fiber product of those two. So start with some base point. And say choose the base point. This one here, and say this one here. And there is orientation on this, of course, on the edges. So consider this point, the base point, it's the one corresponding to this pair of vertices here. From this vertex, there should be an edge. Why should be? Because there is an edge here, and there is an edge from this vertex, and they map to the same edge from here. So that pair of edges forms an edge, and that edge should start from this point. So there is another vertex that corresponds to what? It corresponds to taking what is this vertex? This vertex is the product of this vertex here. It's the pair of this vertex together with what? The ending vertex of this. This pair of vertices gives this vertex. And you continue building this fiber product, right? So what's the end result of it? You can start from this point and see again, there is another edge here, there is another edge here. So that pair of edges corresponds to an edge here. When does the process stop? Yeah, so what? 6 times. You will repeat this process 6 times because 2 and 3 are mutually prime. So what I'm assuming here that m and n are mutually prime. So assume m and n are mutually prime. Then you will need to repeat this procedure 6 times, and then you close up. 1, 2, 3, 4, 5, 6. The same, of course, will happen to the interior circle. You do the same for the interior, and then the corresponding edges will connecting the breakpoints will also be there. This is the fiber product. And there is a map from here to here, and there is a map from here to here as well. Projecting on the first coordinate here and projecting on the second coordinate in here, as we saw last time. What is the fiber? So this is L. It's the ladder of length, what? M times n, right? We assume that they are mutually prime. It's the ladder of length m times n. And what's the reduced trunk of L times, what's the reduced trunk of this graph? So the reduced trunk, let's write it down, of Lm is m. The reduced trunk of Ln is n. And the reduced trunk of Lm sub n, this is m sub n. M times n is m times n. So we see exactly that the reduced trunk of this is exactly the product of the reduced trunks of these two. And that means, so this shows that that the upper bound in the statement of the strength and Hahn-Neumann conjecture and also in the original. And in the statement of the original Hahn-Neumann conjecture is sharp. In other words, it's the lowest possible bound you can hope for. It might be bigger possibly, but it cannot be lower than it's stated in general. So there is an example where the upper bound is attained. And why did I say the Hahn-Neumann conjecture also? Because the original Hahn-Neumann corresponds to just taking one component of the fiber product, but in this case it happens to be connected. So taking one component or taking the whole graph is the same thing. So we cannot really hope for a better estimate than stated. So there is a gap now, right? We know that the reduced rank of the fiber product is at most double the reduced ranks of Y and Z. And we know also that that upper bound cannot be lower than the product without the coefficient 2. It only remains to show that indeed this is a bound. Just the product is a bound. So let's do some drawing first. I'm talking about how one could approach this and what approaches were used. And indeed there was, there were nice ideas there. Using the Euler characteristic was one. And the general idea by Stallings and Emmerich to restate the equation in terms of graphs. Let's try to, so again, assume that we have this this picture. Let's try to try just to prove it somehow by hand, right? What could one try? How can one try and help? And help to understand the problem. And how can one try and maybe fail proving this eventually? So the question is, since the question is it true that the reduced rank of this is at most reduced rank of Y times the reduced rank of Z? Let's try to restate this reduced rank somehow in different way. Kind of try to visualize how it comes from the picture. So given a graph, how can you see it? Just pick some graph like this. We can visualize this by looking at edges. Say, suppose there is an edge here. If I remove this edge, what will happen to the reduced rank? Like on this picture. So the reduced rank, let's count. What is the reduced rank of this, first of all? The usual rank is how many edges should I remove in order to get a tree, a maximal possible tree. Say this edge, say this edge, say the edge here, and then the edge here, for example, right? Then the usual rank would be 4, then the reduced rank is 3. So let's somehow see that number 3 in this graph. By removing edges. But say remove this edge, what happens to the result, the reduced rank? Decreases by 1. What else could I remove to still decrease it? Say I could remove this edge. It also decreases the reduced rank by 1. Then I could remove, say this edge here. Still reduces. And then the result will be 0. I cannot possibly reduce decrease the reduced rank anymore, right? So that is somehow a picture for the reduced rank here. But after you do this, what is left? What's left? It's so that's a nice kind of notion that for which one can draw pictures. So A3, let's give some definitions. So what is A3? You draw a picture like this, right? That's A3. So it's a graph which doesn't have any loop in it. Equivalently, it's the graph which is homotopy equivalent to a point, or contractible, continuously contractible to a point, right? So it's a picture like this. Another nice notion that kind of comes up from these considerations is a flower. A flower is a picture like that, something like this. That's a flower. It's a graph, so i.e. a graph. Informally, one can say it's a graph that has exactly one loop. More formally, one should say that it's a graph which is homotopy equivalent to a circle. Homotopy equivalent to a circle. You see that, or contractible to a circle. So you can just collapse those edges, and the rest is just a circle. So that's a flower. And you see that on this picture, after we remove these three edges here, what remains is a flower. So one can see this on. So draw some graph again, something like that. And then draw some. This graph doesn't have to be connected. Something like this. Consider a graph like this. Say this is a disconnected graph. It has several components. But what is the reduced rank of this graph? You just need to compute the reduced rank of each component. That's how we define it. We define it additively over components. What's the reduced rank of this? That is 0. Corresponds to the trivial group. The usual rank is minus like 0, and then the reduced rank is it's the maximum of 0 and minus 1. That is 0. So we don't remove any edges here, right? That's how you visualize. If you see a tree, there is nothing to remove there. It's already 0. But in here we could remove something like this edge, for example, and this edge, right? After we do this, we are left with a flower. But since we remove 2 of them, the reduced rank of this is 2. What's the reduced rank of this component? It is 0. It is a flower already, and we don't need to do anything. So those are the two special kinds of graphs, the flowers and the trees, where the reduced rank, we don't need to do anything, the reduced rank is 0. One can give an equivalent definition of trees and flowers. Those are exactly the graphs which are connected and whose reduced rank is 0. So so the total would be what? The total would be 0 plus 2 plus 0. That would be 2. The reduced rank of the whole thing is 2 here. Given a finite graph, let's call it say y. An edge. Let's call it sigma in a set of edges. This is the set of edges of the graph y. Sigma is one of them. An edge is called essential if this happens. So this is an example of an essential edge. If removing this edge decreases the reduced rank. So namely, if the reduced rank of y minus this edge. So I'm thinking combinatorially of the graph y. Combinatorially means it's the set of vertices, disjoint union with the set of edges. Just combinatorially. So when you just subtract one edge, the reduced rank of that should be the reduced rank of the original graph minus 1. So that's an example of an essential edge. But what is even more important is an example of an essential, is the definition of an essential set. So a set, an essential set in Y is a set of edges. Let's call it E, which is a subset of edges in Y, such that you generalize this definition. Instead of removing one edge, you remove several edges. You remove all these edges here in this set. So what should we define? How should we define it? Such that the reduced trunk of Y minus this set of edges is the same as the reduced trunk of the original graph minus what? The number of edges in this set, right? That's a natural generalization of this. So think of this being some kind of independence property. It's like saying that a set of vectors is independent in a vector space. And indeed, there is something to it, because one can actually talk about vector spaces, namely Hilbert spaces here. And one can actually make this precise. It's possible actually to restate this in terms of Hilbert spaces and certain dimensions, which we will do later on. So being essential set, it's something like independence of a set of vectors. An essential set. And another important notion is a maximal essential set. Maximal essential set in Y. And you can guess what it is. It just means it's an essential set which is maximal possible. Maximal with respect to the inclusions. And again, one should think of this being the spanning property. It's like having a basis in a vector space, right? This property says it must be independent, and this property says that it must be spanning. It kind of spans the whole space. So maximal essential set. But what's the precise combinatorial definition in Y is an essential set. Set in Y. I can give two equivalent definitions. First is just following the name, right? It's an essential set which is maximal possible. But second, how can we equivalently restate the same definition? First of all, this must be satisfied, right? It must be essential, so this must be true. But under what conditions an essential set is maximal possible? It means that you cannot remove any more edges. For example, the set of these two edges here is maximal. It is essential because removing each edge decreases the reduced trunk exactly by 1. But then after we've done this, we cannot remove any more edges. Say if I remove this, the edge right here, this would not change the reduced trunk anymore, because the reduced trunk is already 0. So it cannot go down. The reduced trunk is always non-negative. So we cannot remove any more edges. But we cannot remove any more edges. That exactly means that after we removed all these, the reduced trunk must be 0. So saying that an essential set is maximal is equivalent to saying that if this property holds, minus E R bar Y minus the number of edges in E, and the additional property that this must be 0. So if it is maximal essential, essential means this equality, and maximal essential means these both equalities must hold. But in particular now you know that so in particular if E is a maximal essential set in Y, then the difference of these two numbers is 0, so those two numbers must be the same. The reduced rank of E is the same as the number of edges in E, the number of elements, right? In particular, this gives a kind of a description of the reduced rank. It's the maximal number of edges that you need to remove in such a way so that at each step the reduced rank decreases by exactly by 1.
Reduced number of Y.
Oh yeah. Sorry. Yeah. Yeah. The reduced rank. Thank you. It's the maximal number of edges you need to remove with such a property that each time the reduced rank decreases exactly by 1. Okay, that's a nice kind of visual description, right? You can draw a picture. Now you take a diagram like this and you try to see the reduced rank of Y, the reduced rank of Z, and the reduced rank of S somehow. See it on the picture and then hopefully prove this inequality. The problem here is that I can take this graph Y and draw a few edges, pick some maximal essential set. I can take the Z, also pick some maximal essential set, and pick some maximal essential set in the fiber product as well. The only question is that those three things might not be related in any way. It's hard to find a relation between them. And that's the main problem. You can visualize this, but it doesn't seem to help really. So what can one do? The idea is to replace this whole picture with an equivariant version of it. So to introduce, the main idea is to introduce group actions. Group actions to the picture. So it becomes not really only a combinatorial problem, but also, again, going back, it's also a group theoretic problem, together with combinatorics, right? With some topological considerations. So how can we introduce group actions? We will do one by one. So we started with a group gamma, then we picked some finite graph. So gamma was a free group, and we can assume that it's finitely generated. So I'm assuming here it's a finitely generated free group. Pi1, gamma is equal to pi1 of x. So we pick some finite graph x, whose fundamental group is gamma. So where is the action here? One can state this in two different ways, either combinatorially or in topological terms. In topological terms, we take the universal covering of X. There is a formal standard construction. So universal means that let's call it x hat to x. It means a covering map from some graph to x with the property that the fundamental group of x hat. Let's assume it's connected, even though again we don't really need to assume it's connected. But let's for simplicity assume it is. The fundamental group of this is trivial. How can one construct such a covering? There is a general topological notion that you saw. A covering, the universal covering, or more generally, a covering corresponding to any subgroup of gamma always exists. But in this case, one can just explicitly draw what it is, right? Since we are working with graphs. So let's try to build this. You take an example. So let me emphasize, you can start with any finite graph, x at all. For example, you could take this, say this graph, consisting of one vertex and two edges. Let's call it x. So what is x hat then? Locally, it should look like this. You pick a base point and you just keep building this graph. Call this A, this is B. So locally it should look like this graph. So there should be an edge starting from this vertex and which is labeled A. It's also true that there should be an edge labeled A that comes into this vertex as well, because locally the picture should be like this. There is outgoing A and there is incoming A. And the same thing should be for B. Here is B, and there also should be incoming B. And we try to build this in such a way so that the fundamental group of the result must be trivial. It means that we build it in such a way so there are no loops in the result. We do not allow loops. So this vertex again maps here, and this vertex locally should look exactly the same. So we continue. Right, continue building this. And then you draw 3 edges here, 3 edges here. And you continue building this graph. And none of these vertices will coincide with any of these vertices. Because otherwise there would be a loop. So we never get a loop. But you continue this infinitely and you get an infinite tree. And there is a map mapping A's to A's and B's to B's. This map is the covering map. And this tree is, of course, since it's a tree, it is simply connected. So it is indeed the universal covering. Another name for what we just constructed is the Cayley graph of a free group. So this is the same as the Cayley graph of the free group gamma. In this case, the rank was 2, say. So I took gamma to be F2. But one can do it again for any Fn. So one could either start with the Cayley graph, or one could start with this and then take the universal covering. The same result. So where is the group here? There is an action. The group acts gamma acts freely on the universal covering, this x hat. This is what we call x hat. So free means, I assume you know the definition. Free means that the stabilizer of every vertex is trivial. In other words, if you have some non-trivial element and pick any vertex, then the action of this element on this vertex, it must translate the vertex. So that in particular means that if we consider the orbits of this action, like in this example here, how many orbits of vertices? How many orbits of vertices here? And what's the action? Maybe we should say it explicitly, what the action is. You pick an element of gamma. An element of gamma, so if you take G in gamma, how do you represent this? It's an element of this fundamental group. So this element is represented by some loop. Wrapping around here several times. You can lift that loop. Say if G is equal to A times B, for example, then what's the action? This is our base point. We selected it from the beginning. And you pick some other point here. And I want to describe what's the image of this point under this group element is. Right? We apply this group element to this point. What's the result? So the idea is you lift this path. This path is AB. You lift it here. So you start from this point. First you go by A and then you go by B, right here. So this is the lift of the path, G. And then you just concatenate this with the path that was representing this point. So I would need to go what? I would need to go up by B and then to the right by A. This point is the result of acting on this point by the element AB. So it's like pre-concatenating this path with the path that represents the group element. So this is the action. The question is, how many orbits of vertices do we have here? So an orbit is, I assume you know, right? An orbit is it's an equivalence class, right? Where 2 points are equivalent if one can be moved to another by some group element. How many orbits do we have? So how many equivalence classes like this do we have? What?
Everything? Every vertex?
Yeah, so every vertex is going to be in the same orbit. So the number of vertices would be just one. The number of orbits would be just one, right? It's a transitive action. Given any point like this and given any other point like this, you can always find a group element that maps one to the other. Transitive action, so the number of orbits is 1. And the number, maybe I should say number of orbits, and the number of orbits of edges again, an exercise, and the edges are moved in the same way, right? You pick an edge here, say, what's the result of moving this edge? You consider, you draw the path from this, from any of the endpoints to the base point, and then precompose it with the element G, say with AB in this example. So how many orbits of edges? Again, any edge labeled A can be mapped to any other edge labeled A. And any edge labeled B can be mapped to any other edge labeled B. So there are exactly two orbits of edges. So we could pick a fundamental domain, for example, but let's talk about this later. Okay, we took the universal covering of X. Or equivalently, this is like picking some Cayley graph corresponding to some generating set of the group. So if I draw it on this diagram, we introduced another graph which covers X here. And then what we do, we take the pullback. This is the formal way of saying this. You take this diagram and you pull it back by X hat. You pull it back by this map. That's the formal way of saying this. Or what one could explicitly describe what the pullback of Z is, pullback of S, pullback of Y. And I will do this in a moment. But let me just say formally. So formally, take the pullback of the whole diagram. Of this whole diagram, S, Z, Y, X, by the map, by the covering map. Let's call it P sub X. P sub X from X hat to X. That's a formal and short definition. Let's see. Y. So replace Z with Z hat, Y with Y hat, S is with S with S hat. This is the diagram that one obtains that way. So let's call this a system of graphs. And let me say that once you consider a diagram like this formally, you can immediately see that you can do the same thing for complexes. One can talk about systems of complexes rather than systems of graphs. For the purpose of Hahn-Neumann conjecture, they all should be graphs, but if one tries to generalize the statement, then it's a good idea to think about more general situation when all these are complexes. One only needs to define properly. You remember this map from y to x and from z to x. Those maps were immersions. So one would need a notion of immersion not only for graphs but generally for complexes. So let me just say that a system of graphs, this formal definition immediately gives you the definition of a system of complexes as well. We only need to define what an immersion is. And let me say this. So what I will say now, it's not related to the original Hahn-Neumann conjecture, but rather it's kind of an attempt to generalize the statement. So for complexes, what would be a notion of immersion? You remember we saw that we said that y to x is an immersion if it's locally injective. Just saying locally injective for complexes doesn't really help. One needs a slightly different definition. But you just notice that the same definition for graphs can be restated in a different way. Instead of saying that it's a locally injective map, we say that it's a map which you can complete to a covering. You can add a few edges and maybe vertices in such a way so that, so in other words, embed this y into a bigger graph such that the map, there is a map from that bigger graph to x which is a covering. So in other words, an immersion, it's a composition of an injective map together with a covering map for complexes. And once you restate it this way, you see that you can say exactly the same thing for complexes. So an immersion y to x between two complexes, cell complexes y and x, is a cellular map, by which I mean it's a combinatorial cellular map. I require that all open cells map homeomorphically onto open cells. A cellular map which can be completed to a covering. That's a short way of saying. The explicit way of saying that can be written as the composition. So y to x, first you include y into y prime, and then you map y prime to x as the composition, where this is the inclusion, injective map, and this is a covering map. Can be written as this for some complex y prime. So an equivalent restatement for graphs, this happens to be equivalent to what Stallings called immersions, but now this generalizes to higher dimensional complexes. In particular, this implies that yeah, and I guess you need to assume, depending on definition, we can assume, let's see. Okay, that's fine. So that's an inclusion. Once you have this notion of immersion, you start with some complex X, you consider the fundamental group, then consider any immersion of this, consider any immersion into here, take their fundamental groups. Consider this fiber product of y and z, and then pull back the whole diagram by x hat. Formal definition. So what does it actually mean? So the explicit, there is an easy explicit description of what those graphs are. Let's go back to graphs. So if x was this graph, then we have x hat. X hat is this graph, the tree. And then suppose we have some immersion, z here and y here. We want to pull them back. And remember that pi1 of y was a. Y was representing the subgroup A. What is the pullback under this map of y? So we want to see what this y hat is and what those maps are. It turns out that y hat consists of so it's the fiber product of y and x hat over x. But this map, let's see. But the fundamental group of this is A. So one can provide a formal argument to describe what y hat is. Or I could just give an explicit definition and then you check that that's the same thing. So the explicit definition is the following. You take x hat and then you pick, so y hat can be constructed as follows. Take x hat, the Cayley graph or the universal covering. Gamma acts on x hat, right? There is a free action. But A is a subgroup of gamma. So A in particular also acts on x hat. So I can take this 3x hat, let's draw it this way, this is x hat, and pick some base point. Let's call it x naught. And consider, so in other words, first I'm going to construct a universal covering of y. That's what I'm pretty much going to do. But I want to construct it as part of this picture. We just pick a point, consider the orbit, the A orbit of x naught. So we get many points here, maybe not all of them. It's just an A orbit. It's not the orbit by gamma, but by A. So this is just a subset of vertices in x hat. And then from corresponding, since A is finitely generated, we just pick a finitely generated, a finite generating set. And see where x naught is moved by only those elements in the generating set. Say it's moved here by one element, moved here by another element. There are finitely many edges that I can draw. So I'm drawing an edge, but what is an edge here? I'm actually drawing a path in x hat. What I drew as an edge here, it's actually a path in x hat. Maybe I should draw it like this. There is a path here. Representing this is x times x naught, where x is in the generating set of A. So I pick all such translates by the generating set and just pick a path using them. So what's drawn here, it's a little tree, finite part of this picture. And then I can translate this whole picture by the group action, by A action. So pick path corresponding to the generating elements, and then translate by the A action. So take this picture and keep translating. So I could translate x naught first here, and then to another point, another point. In other words, I can use the generators to translate, to cover all the orbit of A. Since they are generators, in this way we will cover all the vertices in the A orbit. So we get a graph like this. And since we translated trees and everything happens in a tree, this is a tree, the union of all such will be a tree again. So the union of all these vertices and edges is a subtree of x hat. So let's give it a name. I'm going to use a cursive letter A for that. So A is the union. So what do we have? First, of course, A acts on A. This action by gamma on x hat, if you can restrict it to A, and this tree A here is invariant under the A action. So this is there is an action here restricted from the action of gamma. What else can we say about this action? Since the action of gamma was free, then the action by A on that will also be free. All the stabilizers of this action will be smaller than stabilizers of this action. So they all will be trivial. So it's a free action. What else do we know? Since we started with just a finite number of edges here, and then we translated them by the group, and we covered the whole orbit, that means that this action is co-compact. Co-compact means that the quotient of A by the action of A is finite, is a finite graph. So compact in this case means the same thing as finite graph. So the quotient is compact. And also this graph A is a tree. So going back, what is y hat? Y hat happens to consist of many copies of such A's. So you have an inclusion here of A, of the graph A. It's included here. You can check that, it's just by definition, it's an injective map. There is an inclusion map. What is this y hat? This A is invariant under the group A, but it doesn't have to be invariant under gamma. So we can consider all possible translates of this. And this is what this y hat consists of. It consists of all possible translates of this. So in other words, the picture is as follows. You have x hat, and then you have a copy of A hat, of A here. And then we can formally build, think of this A being a subgraph in here. So by this map here, informally you can think of this A being in here. But now all the translates of this, you formally make disjoint. In other words, this is called the induction. What we formally do, there is a formal notion of induction in like homological algebra or algebraic topology. We induct from group gamma to the subgroup A. So every graph A we replace with several copies of A, one copy for each for each left coset of A in gamma. But let me just draw the picture here. So we can just formally define this. So y hat, by definition, let me write it this way. It's the induction of A from gamma, never remember which way it is, from A to gamma. Induction from the subgroup A to gamma. By definition, this formula means the following. you take all left cosets of gamma of A in gamma, and then you just formally take the Cartesian product with A. In other words, it means that we take one copy of this graph for each left coset. So we just multiply this graph as many we have left cosets there. This is what I mean. All those copies, they correspond to left cosets of A in gamma. And now we have the group action. This is what y hat happens to be. If you unravel that formal definition that I gave, this is the explicit description of this. I call this a leafage. It's an English word that no one knows. And the name comes, as you can guess, it's from the leaf. It's like a poetic term for foliage. And the leaves, in this case, are the components of this. So this is a leaf, a leaf, a leaf. What is a leafage? A leafage, one can give a general definition. A leafage is a map which between cell complexes, which it doesn't have to be injective, but it's required to be injective on each component in the domain. So a leafage is a map injective on each component, connected component of its domain. It's a map between cell complexes in general. And you can see, again, either from this formal pullback definition or from this explicit description, is that this is a leafage. This map from y hat to x hat is a leafage. The same thing we can do for z hat. Z hat is constructed in the same way. You pick a point in x hat, consider the b orbit of that point. Then draw the tree kind of covering that orbit. You have an action of b on that component, which we call b. And then you take the induction of that component from b to gamma in the same way. This is what y hat is. So this is a leafage, and this is a leafage. What is s hat then? Again, formally by definition, it's the pullback of s to s hat under this map, from under this map here. That's a formal definition. But now you can describe explicitly what it is, right? Pick just one component. So one component is here. You can think, so A is part of this. It's one component. Here you also have this B. That's also one component of z hat. And you can see that s hat is the fiber product of y hat and z hat. One can give several equivalent definitions for s hat. We define it to be the pullback of s under this map. And it's a little exercise to check that equivalently it can be defined as the fiber product of these two over this map, formally. But what is the fiber product of A and B over x hat? A now includes injectively in here. B also includes maps injectively here. You have two injective maps. What's the fiber product of two injective maps? If you have something, and then you have an injective map, and then part of it also you have an injective map. What's the fiber product of these two injective maps? No. Sorry? No. The quick answer is no. Let's follow the definition. Fiber product consists of all points, all pairs of points, which map to the same thing. So they are required to map to the same point here. How many pairs like this can you find? Given a point here, how many pairs like that can you find? One, or maybe none. Right? Maybe none, because it doesn't have to be surjective map. But at most one. It means that for every point in here, you will find at most 1 point representing this point in the fiber product. At most one. So in other words, the preimage of this point in the fiber product consists of at most 1 point. In other words, fiber product is injective into here. That is to say, the fiber product of two injective maps is injective. Okay, so what's the picture? You just map it here, and then take the intersection. You consider this as a subspace in here, consider this as a subspace in here, and then take the intersection of them. This is what this fiber product is. In other words, if the map is injective, the fiber product corresponds to intersections. So going back to this picture here, so A is you can think of being a subset in here. B is also, you can think of this being a subset in here. And what's the fiber product of just A and B? It's the intersection of A and B in here. So we took a tree for A, we took a tree for the subgroup B, and we just intersect them. It's an intersection of two trees. But then you do the same thing. So you take that intersection in here. That is one part of S hat. Is it everything? It's not everything, because we can take a translate of A. Instead of taking A here, we could take some translate. That would give you what? It will be another copy of A times B. Take another translate. Everything you will multiply with B. With B also we can take a different translate. In other words, we just pick any component of Y hat here. We pick any component of Z hat here, and then for each pair like that, you take their intersection. So S hat consists of all intersections. S hat consists of the components of S hat are all possible intersections of translates of A with the translates of B, with those of B. So take any component here, take any component here, take their intersection. That gives you a component of S, and you just take a disjoint union of all such for all such pairs. So that's a nice picture. The only thing I want to emphasize is that we have an action of A on A that induces, let me write it here, gamma acts on X hat, but it also acts on Y hat. What is the action? We know that the subgroup A acts on this component. What is the action? What's the natural action of the group gamma on this whole thing, on this induction? One can define it formally. Formally, it means that you pick an element of the group, and you represent it as what? You can represent it as some element of A times some representative of the left coset. You let the representative act on here, and you let the A component act on here. So there is a formal definition. If the group A acts on here, then you can extend it to a gamma action on this whole thing.
It's not canonically defined.
It's not. It depends on the choice of representatives. Yeah, but there is an action. This induces an action of gamma on Y hat. So in other words, so let me write it again. Gamma acts on Y hat. What it does, it permutes these components. The action permutes these components. And what is the stabilizer of A? This happens to be exactly the subgroup A. So there is an action here. The same thing, we can define the group action on Z hat. And it also, since this S hat is the fiber product of these two, there is an action on S hat as well. and on S hat. So that's how we introduce the group action into the picture, and I'll continue next time. It's time to finish. Thank you very much.